Hey, mathletes. Welcome to Oblique Asymptotes or slant asymptotes. Now, sounds kind of weird, right? Like, what's an oblique asymptote? Well, if you think of the asymptotes that we've considered at this point, well, we've had the good old vertical, we've had the good old horizontal. Well, if you think about kind of like the angles of those things, 0 rads and pi half rads, well, there's everything in between. So today we analyze an oblique or slant asymptote. Not going to be that difficult at all, friends. I don't think. So what we're going to do here is we're going to look at this crazy looking function. And I want to use long division to determine the quotient and the remainder. So you maybe haven't done this in a while, but the one thing I want to think about maybe even before we do that is I know this thing has a vertical asymptote at x equals -3. But I want to notice that this thing does not have a horizontal asymptote as well. Because if we let the limit go to infinity of this, so we would divide by the highest power we see in the denominator. So we would end up with this in the numerator. We'd end up with that in the denominator. Well, as x goes to infinity, these two values would go to 0, but this first value would go to positive infinity. So that tells me we do not have a horizontal asymptote. The other way I can tell from a horizontal asymptote, if I have a horizontal asymptote, is I notice right off the bat that the top has a larger degree than the bottom. And so that's why we end up with this 4x. So in this case, I know we don't have a horizontal asymptote. So what I want to think about then is, well, maybe if I don't have a horizontal asymptote, do I have something different? Do we maybe have a slant or oblique asymptote? All right, let's figure that out. So let's go hot pink, and let's do some long division. So some of you immediately are saying, whoa, why can't we use synthetic division? Okay, we can use synthetic division. But the problem with synthetic division that we might come across is what we end up dividing by down here. If it's not a linear function, if it's, say, we're going to divide by a quadratic, then synthetic division is going to fall apart. So even though some of you like synthetic division, what I'm asking you to do is to not use it, because synthetic division does not always work. So we are going to use long division. And it's not like synthetic division saves you that much time, okay? So again, all I say to myself is, what do I multiply x by to get 4x squared? Well, 4x. So 4x times x is 4x squared. 4x times 3 is 12x. Then remember, with long division, what we do is we subtract. So 4x squared minus 4x squared is 0. Minus 4 minus 12 is minus 16. We bring down our next term, and we just repeat the procedure. What do I multiply x by to get negative 16x? Well, negative 16. So I get negative 16x minus 48. And so at the end of this, I get a remainder of just 45. So determine the quotient and the remainder. Well, what we just did was we just rewrote y1 into this form. We rewrote it as 4x minus 16. That's how many times x plus 3 divides into 4x squared minus 4x minus 3. Plus, we have ourselves a remainder, 45 over 4x over x plus 3. Okay, that's what we didn't have, didn't go in all the way. That's our remainder. That's our quotient. Okay, well, how does that help us find horizontal asymptotes, or slant asymptotes, I should say? Well, let's look at the graph of this. So we rewrote this first off as 4x minus 16 plus 45 over x plus 3. Okay, so we rewrote it in a different way. Really, those two are the same. But now, if we go and graph each of these separately, what I've got here in red is the linear function, and what I've got in blue is the original function. What do you notice? The blue function is getting really, really, really close to that, what I've got in red, the red function. And that is the line 4x minus 16. So when we take the long division, what we end up with is an easy way for us to find the slant asymptote. Because remember, when we find our horizontal asymptotes, we let x go to positive and negative infinity. And as we do that here, as we let x go to positive or negative infinity, our graph will approach this line. As we let x go to positive or negative infinity, that would go to 0, wouldn't it? And we'd just be left with whatever positive infinity, in this case, as 4x minus 16 goes to infinity. So this line that we end up with is known as our slant or oblique asymptote. So an oblique asymptote is a non-horizontal line which the graph of a rational function approaches as x goes to positive and negative infinity. That's it, friends. So when I look at something like this example here, I mean, first off, it tells me to find the slant asymptote, so I know what I'm doing. But how I analyze this if my teacher didn't tell me that? So what I say is, look at the degree of the numerator is bigger than the degree of the denominator. So I know I don't have a horizontal asymptote. In fact, what I now know I have is a slant asymptote. So what I'm going to do is I'm going to long divide this. And again, I want you using long division because synthetic division can fail us. It doesn't always work. Okay, then I say to myself, multiply x by x to get x squared, right? Subtract, bring down our next term, repeat. That would just be plus 1. 1 times x is x. We subtract, we get 0. We bring down our next term, we get a 1. Now what I'm going to do is I'm going to rewrite f at x. F at x is what it is originally, or it's also this. The quotient is x plus 1, and we have a remainder of 1 over x. That's the other way to write this function. Now, as the limit goes to either positive or negative infinity of f at x, what'll end up happening is this part here will go to 0. And this part here will go to positive or negative infinity. Okay, that is the equation of our slant asymptote. So our slant asymptote has an equation of y is equal to x plus 1. All right, so as soon as I recognize that the degree of my numerator in my rational function is higher than the degree of the denominator in my rational function, I immediately look for a slant asymptote by doing long division. There it is, friends. Super cool. See you another time.